Okay, so let's jump into our love affair with linear regression. We love it, right? It's a simple algorithm. It can do so much. Very easy to understand. It has two interpretations, both probabilistic and geometric, right? Which is very useful. And we know how to solve, how to learn the parameters from given some training data, right? But there are a lot of issues. So we love it, but we can also hate it big time because it has a lot of these small issues that really prevent us from using it for practical purposes. So there are a lot of holes in linear regression, which we'll discuss today, and then we'll also discuss how to fix them. So it's not like there's no fix for those issues. It turns out that for every issue that we are going to look at linear regression for, there is a fix, all right? So maybe today and the next class is what we are going to talk about. And the one thing you need to understand when we discuss linear regression is that a lot of these issues, which are listed over here on the slide, are true for other machine learning algorithms as well, which means that if you understand how to fix these issues for linear regression, you can use similar philosophies or similar principles for other machine learning algorithms. So there's nothing specific to linear regression by itself, but general class of machine learning algorithms that work in the same way. All right, so let's get started. So issue number one is that this is something that a Bayesian would complain about, is that linear regression, the form in which we learned the parameters, especially using the probabilistic interpretation, does not allow for a prior, right? If you remember when we did this coin toss example, we were trying to estimate the parameters of a coin, the theta for a coin. We said that one way to do it is just doing the likelihood estimation, which also we saw for linear regression, is that you are given some training data and we try to find what is the best W which maximizes the likelihood, right? But as noted Bayesians have talked about, that there is need to also incorporate a prior on these parameters, because sometimes your data might not be enough, or you might not trust the data completely, and you want to bring some prior information into the whole estimation process, right? So of course, what we saw last time for linear regression, the Bayesian sort of way of estimating the parameters, right? So this equation, this we get by maximizing the likelihood, right? Now we want to see how can we make it Bayesian, right? Now we know how to do Bayesian, right? We know when we hear the word Bayesian, essentially what we are talking about is some way of putting a prior probability on your parameters and then incorporating that in the learning process, right? So the first thing we're going to talk about is what we call Bayesian linear regression. And we will see that there are different flavors of this, and we'll see what they mean, right? So harking back to the MLE estimation, right? So in MLE, what we do is we compute, let's say D represents our training data, right? So this is training data in which you have X's and Y's. And what we do in MLE is we compute the log likelihood, which is nothing but the PD given, PD given, or let's call it log likelihood. Log likelihood of D given your W, which is your weight vector, and your sigma square. And we try to maximize it. So arg max of W and sigma square. So values of W and sigma square that maximize our log likelihood. So this is MLE, right? Now what happens if we want to incorporate the what happens if we want to incorporate the prior on this? So what we do is we assume a prior on W. So for this discussion, we'll ignore sigma square for now. You can put a prior on sigma square as well, which is the variance. But for this task, we are going to assume that this we are going to estimate with the MLE, right? So we're going to ignore this. We'll focus on W because that is more interesting. That's more important, right? So we want to assume a prior on W. Now remember, what is W? W is nothing but a vector with D attributes, right? So W is a vector. Mathematically, we can write it as W belongs to RD. And we are assuming that D also contains the bias term. So W is a vector. So what kind of prior can we put on W? right? We can put a prior on W, any distribution which generates samples of this form, right? And we have seen one, which is a multivariate Gaussian. So multivariate Gaussian is an appropriate prior. Right? Because we know that a multivariate Gaussian can generate samples which you can use as W. Okay? So what we essentially are saying is that we have some prior probability of W, right, which is given by a multivariate prior, right? And we are going to assume that this prior has some prior probability mu 0 and some prior covariance matrix sigma 0, right? So this is going to be a d cross 1 vector because it's representing a d cross 1 random vector, right? And this is going to be a d cross d covariance matrix. So prior is something that you specify. You don't learn that, right? And now we know how to compute P of d given W, which is just the likelihood. So now we can now apply the Bayes rule, right? And we can say P of W given D. So this is prior distribution on W. This is what we call posterior, right? So posterior means that once we have seen the training data, what is our revised estimates for W? And that is going to be nothing but P of D given W times P of W, right? Divided by the sort of the integration. So because these are all these are continuous values, so there's no summation here. This is just going to be P of D given W, P of W, dW, dW. Right, this is to ensure that this is a probability, right? Okay, so now comes the question. Well, it's not just to ensure, but this is how the Bayes rule works, right? So this is just a simple application of Bayes rule. Now, of course, we know the form of each one of these. So we know the form of this. This is nothing but the joint likelihood, right? This is just the product that we have worked with in our estimation earlier. So if we go back here, when we were doing the MLE, remember when we wrote out the MLE term and then we sort of maximized it. So that is what is PD given W over here. This is coming from here. We know what this term is. So we can write the mathematical expressions for all of them. This, and inside this as well. And we can do the integration too, right? And it turns out that if you work this out, right, this will be same, this posterior will also be a Gaussian with some mean and some covariance. And why? The reason is because the prior is a conjugate of the likelihood, right? That's we have seen that before, that whenever that holds, that your prior probability distribution is a conjugate of how you compute the likelihood, because the likelihood also we are assuming that they are all Gaussians, right? And here also they are Gaussians, which means that you start with a Gaussian and the posterior is also a Gaussian, a multivariate Gaussian. Right? So, and what will be the expression for that Gaussian? Essentially, when I say it will be a multivariate Gaussian, the question you need to ask is what will be its mean vector and what will be its covariance matrix, right? And I will not go into that detailed derivation, but if you look at the class notes, we have done that. But essentially, at the end of it, you will get some mean, which will be a function of the likelihood as well as the prior, and some covariance. Okay, so that is how you derive this. So this is a Bayesian linear regression. So let's go back. Any questions so far? I'm going to skip some of the mathematics here because that's not central to what I want to discuss. Okay, so what we do essentially is, I have to say one more thing. Now in practice, what happens is that here, this is our prior, right? But in practice, what we do is we assume that our mu 0 is all zeros. It's a vector of zeros. Why? Because basically what we are saying is that the prior probability assumes that our W vector is centered at 0. So that's our prior probability. And we also assume that sigma 0 is essentially a diagonal matrix. Okay, so it's a diagonal matrix in which all the terms inside that are exactly the same. Okay, so this is an assumption that we are going with. Essentially, what we are saying is that we don't know anything about W. So the most reasonable prior we can put on it is that we assume that W is centered at the 0, 0 mark, and it has some spherical covariance around it, or spherical variance, right? Which is given by this. Mathematically, you can also write it as sigma tau square I, where I is essentially an identity matrix, right? So in matrix algebra, you must have seen an identity matrix which is just zeros and ones. So identity matrix is analogous to the number 1 in matrices. So multiply anything with the identity matrix, you get the same matrix again, right? So this is what this is, right? So in practice, this is what we assume, but in reality, there is no real, I mean, nothing is stopping you from making some other assessments about mu 0 and sigma 0. So you can treat it as something else completely, and you can model this also as something else. But here, in practice, what folks have done is that they have used this simple prior, where they assume that mu 0 is 0 and sigma 0 is this, right? So let's sort of informally look at the effect of that. All right? So we're going to assume that D is 2. Okay? So we are essentially assuming that the data is in two-dimensional plane. So W is going to be in R square. It's going to be, it has 2 elements in the vector, and all your x's are also going to be in R square, right? So what we are going to do here is, let's assume that this is your W. So this is W1 and this is W2. So we're going to assume that W vector is represented as 2 quantities, W1 and W2. So geometrically, you can represent it in a 2-dimensional plane, right? So what this prior assumes, you have a question? Yeah, so I'll come to that. So when I say that x is R squared, that actually means that your observation is just one-dimensional, and other one is going to be a bias term. You're right. So there are two basically there are 2 ways you can represent things. One is you can represent your W in this 2-dimensional space, and this is going to be your x. This is going to be your x and y. So this is y is the output and x is your input, right? So the data could be like this. So this is your data. This is your training data. Now, of course, when I say x is R square, basically this means that x is equal to 1 is equivalent to 1 and x. So there's a bias term there as well. So here is your training data, and here is your W. Okay? So what we do with the prior is that we assume that your W is centered here, right? Because this is 0, 0. And there is some, essentially you're fitting a 2D Gaussian there, right? So what you're saying is the probability of W from the prior probability is highest here, and then it kind of goes down. So this, you can think of this as tau square, right? So this radius. So essentially what you're saying is that without looking at the data, I believe that W is right over either here or somewhere around here, and the probability is given by the PDF of a Gaussian, right? Now what we do, when we look at the training data, right, this is our D, then we fit a line or we do whatever our MLE, we get a new estimate for W, which could be somewhere here. We don't know where it depends on where is that gone, here. So this will be what I call my W MLE. This is what I call is my W prior, right? What the Bayesian approach does is that it computes like an average of these two. It says, okay, my MLE, my training data is telling me that W is going to be here. Now remember that MLE gives you a point estimate, right? MLE does not give you a distribution. So MLE says, bam, there is my W, right? Whereas what prior says is that it could be anywhere here with a high probability of being here. What posterior does is that it computes some kind of an averaging and says, okay, my prior is saying it's going to be here, my data is saying it's going to be here, So maybe my W is somewhere here with some distribution over there, right? So that is the effect of this Bayesian terminology, right? Okay. So now the next question comes. Ooh, that figure became messy. Now the next thing that comes is how do we use it, right? How to use. So now we have already. Now what we have is instead of a point estimate for W, which Emily used to give, we have a distribution, right? Now how to use it? The posterior, the P of W given D, which is a posterior on W, for predictions. Because remember, what do we need W for? We need W to get Y star for a new W X star. All right. So of course, in the case of MLE, what we did was for MLE, the P of Y star given X star is basically a normal distribution centered at WMLE transpose X star and sigma square, whatever that MLE is. Right? So this is what MLE gives. Now and that we can do because we only have one value for W. That's what MLE gives us. But what do we do when we have a distribution, right? So one thing we can do is we can take the map here, which is the most likely value for W from this, which is called map estimate. And of course, for a Gaussian distribution, the most likely value is at the mean, right? So for map, P of Y star given X star will be and since I said that we are not going to do map for any estimation for sigma square, that will stay as the MLE, right? So we can use it like this, or we can do that full Bayesian treatment. If you remember the full Bayesian treatment, we are going to assume every possibility of W, but we're going to integrate over all possibilities and multiply with the probability of that W, right? So that's the full Bayesian treatment, where we say that P of Y star given X star is actually P of, so actually it's going to be the probability of any W times probability of this W itself given your data times dW integration over all possible W. Right, so this is the full Bayesian treatment where we say that, okay, I'm not going to assume that this is my one W value. Anything could be W, but then I'm going to use that W, get the prediction, but I'm going to weight it by the probability of having that W, right? So that is sort of the full Bayesian treatment. And it turns out, because Gaussian is such a beautiful distribution, is that even this whole quantity that looks a little intimidating, right, also turns out to be a Gaussian, right? Also a Gaussian with some mean and some covariance, right? And this is where I do not go into the details of how to derive this, but you know all the forms, right? You know all the forms, so we know what this is. You can write it out mathematically. You can write this out mathematically, so you can do an integration in principle, right? But if you pick up any book, I think in the class notes I have the final expressions as well. Okay? Any questions so far? Yes. I'm sorry, this W? So basically what we say is that since we are not assuming any point estimate for W, we'll consider every possible W in the world. So think of it this way, that here, right, this space tells us where W can be, right? And W can be anywhere in this two-dimensional space, yeah? When we do MLE, we assume that W is just this. When we do map, we assume W is just this. When we do this full Bayesian treatment, we consider every possible value of W in this continuous space, so infinite possibilities. So that goes here. Then we multiply with the probability of that W. and then we integrate it over all possible values of W. So it's a sort of an integration over all possible values of W. Of course, we don't do that explicitly. When you expand all of these mathematical expressions, you can do the integration because we know how to do analytically some of this integration. All right? Yes. All the weights would be the same. So map essentially will give you the mean of this posterior, right? So this could be anywhere. So the W1 and W2 for the map need not be the same. You see what I mean? All right. So that's what the map gives you, whereas the Bayesian treatment, we consider every W and then we do an integration. All right. Any other questions? All right. So moving on. Okay, so in the slides you will see a slightly different way I sort of treat this is, so let me just go through the slide so that you don't get confused. So remember, to do the Bayesian regression, what we do is we put a prior on W, right? Which can also be considered as a penalty that we are putting on W, especially when we are using that 0 tau square prior, right? So when we are putting this prior, essentially what we are saying is that even if your training data is saying your W should be somewhere, your prior is trying to pull it towards origin, right? So that is the effect of prior. So later we will see that this also kind of means regularization. If you remember in neural networks, we had this regularization term, right? And the effect of that regularization was that it would force W's to be smaller. Even if your fit on the training data or your error on the training data was being minimized by a W which would be very high, this prior and the lambda that is associated with it would try to bring it towards 0, right? That is the same effect that this also has. That's why I drew this figure over here, is that your MLE or your training data would say that W should be here, it's far away from origin, but your prior says no, it needs to be close to 0, right? So that is sort of the effect. And what controls, so remember in the regularization of neural networks, we had that lambda parameter, right? The tau here, this tau value has the same effect. So if you put tau to be very small, right, what will happen is that the results that you will get, the W posterior of W that you'll get, will be closer to 0. Because what you're saying when you're saying that your tau is very small is that I have a very high confidence that your W should be near the origin, right? So that's why when you compute this, and that, I mean, I'm not just saying it, when you compute this, where is that? Right. When you compute this value, right, you will see that the tau will have a direct effect on how much should it come close to the origin, right? So that is the effect. So we're kind of putting the penalty. The reason I'm talking about this is that, remember that there are two ways of looking at regression, right? One is geometric and one is probabilistic. And in both we have this way of regularizing, and both have kind of the same effect, right? So let's go here. All right, so we talked about all of this, right? So the posterior is also a Gaussian, magically. And it's not a magic, it's because the prior and the likelihood were conjugates of each other. So posterior is also Gaussian. And you can also compute the map estimate. Remember, what is a map estimate? Map estimate basically maximizes your posterior probability, right? The value of W at which your posterior is maximized. Now that actually can be written out as this. So let's do that quickly here. Okay, so map estimate. So the map estimate is the value of W at which the posterior probability is maximized, right? So argmax W of P W given D. That's your W map. Right, that's your W map, right? So this you can write as, essentially you're trying to maximize the log likelihood. So the log likelihood is given by this, right? Over all I, yi times the probability of W. Right? So prior probability, likelihood, and there's a division by sort of this integral over all W, right? But we ignore that because in that, since you're integrating over all W, W disappears from that expression. So that doesn't really matter anymore. So we can just write it as arg max of W over here, right? Now what will happen is that if you look at this term, this we have looked at, right? So this is the joint likelihood. So this will look like this. It is 1 over under root 2 pi sigma exp minus half 2 sigma square yi minus W transpose xi square. So pi of this I equal to 1 through n times the P of W. Now since we assume that this is also a Gaussian, so this will be 1 over 2 pi, right? D by 2, whatever D is, tau, the determinant of the covariance matrix, which is just going to be tau because so it's the sidebar here. So we are going to assume sigma is just sigma square I, right? So it implies that the determinant of this is just going to be sigma square, sorry. And then here we do the raised to half. So this is going to be tau, and exp minus tau 2 tau square whatever W, right? Because actually it should be W minus the mean, but we are assuming that mean is 0, so that's why it's just W square, right? Or W transpose W, sorry, W is a vector. All right, so this is as clean as I could put it, but this is what it is. This is the thing, and then we want to maximize this, right? So now what we will do is we'll sort of take the log of this just to avoid all these products, right? And then what it will mean is that W map, and I'm going to ignore, so this is sort of a skip here that you can, when you go back, you'll figure it out. Taking log, ignoring terms that do not depend on W, which means that W will basically be arg max of W, and of course this term depends on W, right? So this will be something like summation, then log will make the product into summation, so log of and there will be a 1 over 2 sigma square yi minus W transpose xi square, right? Oh, what did I do? Sorry, there's no log because there's an exponent there, plus 1 over 2 tau square W transpose W. Actually, it will look like this. All right, all I'm doing is I'm just taking a log and then expanding stuff and then ignoring anything that does not depend on W, right? So then what we are going to do is we are going to maximize this. All right, and what you will see, actually there's a minus term outside everywhere because there's a minus in the exponent. So we are trying to maximize this, and we can, if we ignore the minus, which it is equivalent to W map is arg min. If I ignore the minus term, that we need to minimize this sum. Now the reason I wrote it like this is now suddenly this looks like we are trying to minimize the loss, right? So if you remember a geometric interpretation, this is how we write out our loss, right? So we are trying to minimize the loss, but we are also adding this term here, which is nothing but the magnitude of your W, right? So this can also be thought of as a regularization parameter. So this is the effect of this term is just doing regularization. So we started with a probabilistic interpretation of the posterior, and then we rearrange terms, and we see that that is nothing but doing the least squares estimate, but with a regularization. All right, so both are equivalent. So Bayesian regression, in which we assume that our prior is a Gaussian, is the same as doing least squares with this regularization term, which is, so this, remember that W transpose W is same as the square norm, right? Because you're just multiplying corresponding terms and adding them together. So you can also write it like this. So this looks very much like what we did in neural networks, except neural networks we had matrices, but we're doing the same thing. We're trying to minimize, we're trying to penalize solutions in which W is very large, right? So instead of going this way, where we started with this probabilistic interpretation, we could have directly jumped to this. We could have said, hey, let's try to find a solution which not only minimizes the error, but also is small, right? So this is what we call ridge regression. And I'm going to come to that later on. But if you directly sort of started with this as my formulation, actually what people do is they also rewrite it as, so this is equivalent to saying that arg min of W yi minus W transpose xi square plus, I'm going to ignore the 2's because 2's are, they'll go away, the constant, and then I'm going to move the sigma square here. So sigma square over tau square W transpose W, right? So this now starts exactly like what we do in ridge regression, which I'll introduce later. So ridge regression is essentially doing least squares with a penalty on your W, which is like this, and the posterior, or the Bayesian regression also kind of does the same thing. So they're equivalent in that way. Any questions so far? Whew, all right. So just to show you some results without going into the details, as I said earlier, right? So posterior for W, when we assume that this is our prior, also is a Gaussian distribution. So this is the posterior distribution, and the mean of that distribution is given by this quantity, and the variance is given by this. So now one thing you will notice is that, remember, in the case of just the probabilistic linear regression, the form of your the probability that you got, right, was x transpose x inverse xy, right? Remember that over here, x transpose x inverse x transpose y. In this case also it's the same. There has to be x transpose here, I'm sorry. It's the same, except that we have added this extra term inside. So it's very similar to your linear regression, but adding this extra term that is coming because of the prior. So essentially what you're modifying your posterior. So as I said in my diagram, right? So you start with your prior over here, W at the origin, and your likelihood says it's over here, but then you try to bring it closer. And the effect, and this is the effect of tau square. So if I change my tau square, my estimate for W will also change. All right, and then these are all how to now get the prediction. So you can use the MLE, you can use the map, or you can also do our full Bayesian treatment, which we love. Okay, any questions so far? So that is end of one sub-module today. Okay, so the next thing we want to do is look at some other issue with linear regression. All right, so the first issue was that it is not Bayesian, but we solved it by incorporating a prior. The next issue we want to talk about is that it is too simplistic, right? Because it's a linear relationship. It assumes that y and x are connected through a linear function, which is parameterized by W. So in geometric sense, what it says is that given some points, it tries to fit a line. But in sometimes, what could happen is that line might not be enough, right? You might want to fit a curve. But linear regression in its plain vanilla form will force you to fit a line, right? So let's say this is your data. So this is your y, this is your x, and then you'll incorporate a bias as well. So let's say this is your data set. So these are your y and x. Now, if I do plain linear regression, it will try to fit some line which will minimize the error or maximize the likelihood. It might look like this. But you can see in this example that it might be better to actually fit a curve, a smooth curve like this, and that would have a lower error, right? But linear regression doesn't let you do that because it makes that assumption. So now, how do we learn non-linear curves with linear regression? So the way we do that is by introducing this notion of basis functions, right? So what basis functions do is they take your original data, let's say this x, and they replace it with multiple functions of x. Okay, so for example, let's say your x was something. Your x was, so this was your data. X was let's do here. So x, when x was 1, y was whatever 3, x was 4, y was 9, x was 3, 5, y was 12, 6, and so on, right? So let's say this is what your training data. And let's say we are not happy with the line that linear regression gives us. So what we can do is we can replace our training data and say, instead of x, I'm going to write x squared. All right? So this will be 1, 16, 25, 36, 81. This will stay the same. And now suddenly I've changed my data. I've changed my data into a new space by applying a basis function. So the basis function we usually represent with this phi. So one basis function is x squared in this case, right? So now if we learn a linear regression on this new data set, right, what will happen is that you will learn a line. Of course, linear regression always learns a line. But when you bring that line back into the original space, because the line will be in this new space, right? When you bring it back, it will look non-linear. So that's the magic of this basis function expansion. So the idea is this: your data lies in this space, right? This is your x and this is your y. Now suddenly you change your x-axis. You made it the square of x-axis, and now it's a new space. There you try to fit a line. When you bring that line back here, it will look non-linear. So that's the whole magic. And using that, we can learn non-linear functions. So I'll show that to you with an example. But the general idea is this, that you replace x with non-linear functions of x, okay? And then the model will still be non-linear in W. So now what we are trying to do is we are trying to say that Py given x is not W transpose x, but it is actually W transpose phi of x. And the beauty of this is that you can have as many basis functions inside as possible. So you can have one which just does x squared, one with just x cubed, x to the power 4, and so on. So you can expand it anyway. In many practices, what people do is that they apply this vector. They say, I'm going to replace x with x to the power 0, which will just be 1. So that's kind of like putting the bias. Then x to the power 1, x squared, and so on till x to the power d. D can be anything. So something that you specify. In fact, in the assignment, I think I use p because we use d as a dimension. So, but anyway, so what happens is, and we'll see that when we increase our d, our p also, the complexity of the curve will increase. So let's look at that. Any questions so far? Okay, so let's go to this workbook. Of course, this is our data that, or maybe we'll have a new data set. Sorry, let's go back here. All right, so let's say this is my data, right? This is my data, and I want, if I fit a line, this is what the line will do, right? This is not a very good fit, of course. What you can do is you can expand this. So you can say, instead of d, I'm going to add some polynomial features, all right? So in sklearn, actually, there's a way to add polynomial features, and let's play with that. So you can assign the degree of anything. So when I say degree of 0, what that means is that I'm going to replace x with a vector which just contains x to the power z, right? So of course that's stupid. Sorry, what's going on? Let's make a new cell here. Too many things going on there. So we're going to assume we're going to generate some data here, right? And I'm going to generate data in a nonlinear fashion. So this is a generation process. So I'm just applying some cos function and pi and so on. And then this is my x, right? So for now, let's just look at x first. X XOR. Comment something else? Oh, up here. Sorry. All right. So this is my data that I generated, and this is sort of a straight line that I try to fit, just basic linear regression, right? Now what I try to do is that instead of doing linear regression, I try to first do a basis function expansion, which means that I'm going to replace my x's with some set of basis functions. So for example, here in sklearn, there's a way of adding polynomial features. Okay, so this is what it do, and then I can add some polynomial features, and then I can also pipeline.fit. And then what I can do is sorry about this. What do I do? Oh, pipeline.predict. All right. So this is one very cool thing about sklearn is that you can construct these pipelines. I think one of the TAs in one of the recitations, at least for the undergraduate section, is going to go over this. So the idea is that you have some data and you want to do a chain of things. You want to first do a basis function expansion, then you want to apply a linear regression on that, and maybe you want to do many more things after that. So you can construct this pipeline. So that's exactly what's going on here. So you construct a pipeline in which first you do some polynomial feature expansion, and then you add a linear model to it, right? So what you see here is that here I've added a 2 basis function expansion, so 2 power 2, right? So here essentially what's happening is that instead of x, we are replacing it with 1, x, and x squared. So suddenly the data is 3-dimensional now. Now we fit a linear regression on that, and then we bring back the predictions into the original x space, and this is what it looks like. So it's a much better fit, right? So that is the idea, and then you can change it. So for example, if I just did degree equal to 1, then that's just what it was, right? So we are essentially replacing, we're just doing linear regression here. The basis function expansion is just identity. Oh, I wanted to do 0 as well, which means that you're just replacing x with just 1, which means that it will just learn a flat line, but apparently it's not doing here. But as you increase the degree, you'll see that your complexity of this curve starts increasing, right? So with 3 it becomes like this, with 4 little more, let's just jump to 20, and then you'll say, oh, it just becomes really non-linear. In fact, so when it, let's say 10, right? So you'll see that it starts sort of making it more squiggly, and what will happen is that as you keep increasing your d, your line will start sort of hugging the data more and more. So you can see at some point, what you will see is that for some very high degree, your line will actually go through every point. So it will be a terrible overfitting issue. So the point is that through this basis function expansion, now suddenly you can convert your linear regression into a nonlinear regression, right? With arbitrary complexity, right? You can make it go as quickly as you want. Right? Of course, that's not a very good thing, because we have seen that before, is that you do not want to do too much of overfitting, because this might lead to poor generalizability, right? And later on, we'll see how to control for that. But the main point is that the basis function expansion business allows you to fit really complex fits, all right? But the next question is that we want both. We do want a little bit of non-linearity, but not too much. We do not want our data, we do not want our solution to completely sort of go through every data point. So try to minimize the training error, right? So for example, in this case, your training error is actually 0, because your line or whatever your curve is exactly going through your every data point, which means that y and w transpose x are exactly the same. So your error is 0. But clearly, this is not a good solution, because number one, it might lead to, because this is doing overfitting, right? So it might lead to poor generalizability, because this is a curve. Suddenly now you are talking about a solution which has higher VC dimension. So remember, then VC dimension kind of is proportional to how much your generalizability. So you need more data now. Remember when we did our whole analysis of how much data do we need for pack learnability when we are given the VC dimension? Here what happens is that your VC dimension grows as your nonlinearity grows. So as you introduce more and more and more basis functions, your VC dimension grows up, which means that your generalizability goes down, or you need more and more data to actually learn reliably, right? So it's not a good thing. So how do we control both? Right? Somebody could say, hey, then if you don't want overfitting, then stick with d equal to 1, which means that just a line. But we are not happy with that either. We want best of both worlds, right? So to do both things, what we do is we apply basis function expansion, but we control the overfitting through regularization, right? So that is exactly what I mentioned earlier as well when I was talking about ridge regression. So the idea behind this is that we do not want to use simpler models, because it might lead to underfitting. We want some curvature there, but we also don't want it to go too much, right? So how do we control both? Is by regularizing our model. So we want to minimize our error or maximize our log likelihood, whatever, but we also want to penalize the complexity of our model. All right. So this equation is actually a general regularization philosophy, right? This is not limited to linear regression, right? Any model that you have in which you are trying to learn your parameters, which are given by this case, if you only try to minimize the error, it leads to the risk of overfitting. So we add this regularization, and we have a term alpha or lambda in our assignment, which allows us to control between the two. So regularization penalizes complex solutions, right? Whereas this error favors solutions which give low training error. So this alpha kind of balances the two, right? So what happens so one form of regularization, what I introduced earlier, which we call ridge regression. In ridge regression, what we do is we try to minimize the error. So in the case of linear regression, this will be y minus w transpose x squared. Plus, we also want to penalize large values. So this exactly corresponds to our Bayesian regression with a Gaussian prior, right? There also it had the same form, except here you had sigma square over tau square. So alpha kind of has the same effect as that. So you're trying to minimize your error, but you're also trying to control the size of your W. Because the size of W, and I'll tell you what that means, right? Okay, so this is in ridge regression the exact loss function. So this is the loss from your linear regression, and this is the sort of the effect. So I changed the terminology a little bit. So this kind of represents the L2 norm of your vector. So if you have a vector W, this kind of basically sums up the squares of the values and then takes the square of that. So this, you can write this also as W transpose W. So this is the loss function for ridge regression, which looks very much like Bayesian regression with Gaussian priors. And then in next class, what we'll see is we'll try to figure out how to compute the W. It's not the map estimate actually, it's just the estimate of W under this regularized solution, right? And it will turn out to be this, and this looks exactly like what I showed you earlier. And it also kind of corresponds to linear regression, the loss function as well, except it didn't have this term. So if we put lambda to be 0, which means that we are not regularizing at all, then this part will be 0, and this will look exactly like what you get for linear regression. All right. The effect of this is that it will force your W terms to be closer to 0, which means that, so what will happen is that let's say this was your x, right, and this is your y. Then you applied some basis function expansion, and you said this is phi1 of x, 2 of x. This, I mean, earlier I said these are just polynomials, but this could be anything. This could be sine of x, this could be cos of x, this could be sigmoid of x. It doesn't matter, right? And this is your y. And now you try to learn W. So now suddenly your W will be a vector which will have W1, W2, and so on, WT or WP, right? So now what you're assuming is that your Y is W transpose X, where X actually not X, but a phi of X. So this vector is the phi of X. So what ridge regression does is it tries to minimize these values. So what you will see is that even though you are saying that I'm going to expand my X into this basis vector space, because of the impact of this ridge regression, what it will do is that your W's will be small. And we'll see how it works. But this will, let's say this is your W1, W2, W3, WP. Your W's, it will force W's to be small, which means that because they get multiplied with your phis, right? So phi1 of X, phi2 of X. The effect of that will be that even though you are really making it complex, but because W's are small, the shape of the curve will not be as squiggly as before. Right? So in fact, if you get a time, you can look at this workbook, and this is where what I do. I did that. So I fit a model, and I fit a polynomial to that, but then I do some linear ridge regression, and by doing ridge regression, can't see that. So try to look at this workbook a little bit. But what it shows is that this was your data. This is if you do not do any penalization, and you try to fit two polynomial curves, so quadratic curves. And this is what happens if you put a ridge regression penalization on that, and it will again make it sort of close to linear. I mean, this effect looks much better if you do this. So let's move it to 10. So this is the effect of taking a 10-dimensional basis function, vector, right? So it's very squiggly, overfitting, and this is what happens when you apply ridge regression to that. And this will sort of still make it little nonlinear. In fact, you can control the nonlinearity by this alpha parameter. So if I make it 2, that's that lambda. So it will still be nonlinear, but not too much. So that is the whole effect. All right, let me stop here because next class has to start, and I'll talk to you on Wednesday. Thank you very much.